in 2 weeks, it will be exactly 45 years that I've seen Zakharov first time. And I was 18, and he was 38. Very old man, I remember this feeling. He gave lecture on self-focusing. I remember it very well. I remember how he entered the room. I remember how he started speaking. And I remember this feeling that I want to be his student. I want to belong to this school. And it was not easy because Zakharov was already left Novosibirsk, and I found his students, etc. And then we wrote a book. And I cannot say how much I'm grateful to University of Arizona for this wonderful opportunity. Like Talmud say, you need to honor your teacher as well as your parents on the same level, even more because teachers give you life and teacher give you world in which you live your life. So for 45 years I live in the world, which to a large extent was created by my teacher. And I want to share some of it, of this world, some unexpected doors and passages between different parts of this world. So this 5 lecture will be on subject which is very difficult to pin down. If you say that it's information theory, you would be kind of thinking that you're talking to data scientists or to computer people. If you say that it's statistical physics, then you'll be talking to physicists, but it's actually the same. And what I really want to give you, it's not something which would be tutorial-like, that you can get and different departments teach exactly the same subjects on a totally different language, but people who design self-driving cars, people who study black holes, people who study neuron system or try to understand how brain works use exactly the same technique. And they call them different names, and it took a little bit of time to understand and to translate. And what I tried to give you in these 5 lectures is this panoramic view so that you would see that most of these people taking log of something and sum it and look for some conditional extremum. All of them, most of the time. And so to some extent we understand it's better and better in all this thing which I was taught when I was a student with a lot of paradoxes. It's considered to be very controversial science. It's getting more and more trivial and more powerful. And I want to share this excitement. So how it all started? It started from a very simple engineering question, how to make thermal engine more efficient. So what is thermal engine? You burn something, you get some work out of it, without even detailing how you do it. So essentially, the most idealized description and scheme would be like you have some, which physicists like to call reservoir, which has temperature T1, and you have another reservoir with this temperature T2, and you just take some energy in the form of heat, let's call it Q1, and you deliver it Q2 to the second reservoir, getting some work in the process. And then people notice that you can burn wood, or you can burn coal, or you can burn other materials, and somehow it works differently. So what was this something which restricts the efficiency? And what started as a question about efficiency of burning things and doing work turned in some 100 years into efficiency of communications in the hands of Shannon. Then it turned about questions about efficiency of computing. But it's essentially the same question. And that's what I'm trying to give you this understanding in the 5 lectures, that we're asking ourselves about something efficiency, and eventually it turns out of how much we can say about something we don't know. And because this art of bluffing without blushing is many people involved, that's why it's actually what develops different types. So how you would work it? Okay, you can say that you can measure efficiency by the work that you do, yes, divided by how much you actually spend. But your work, it's Q1 minus Q2 divided by Q1. Okay? That's more or less the way that you So you want this Q2 to be as small as possible, then you will be getting closer and closer to unity. And then a young genius, I just want you to appreciate how much power of abstraction. Just look under the hood of your car. This describes what is under the hood of your car. This beautiful, simple scheme. And because it's so beautiful and simple, it allows you to get something very general. And the idea was that this Q2 somehow restricted. You cannot make it as small as you wish. And how it's restricted. And this young genius, Sadi Carnot, who died young, and most of his things were burned, but then his brother actually served his little notebook, wrote the following inequality. He says that this is restricted by Z. Okay? So something about an energy that you deliver divided by temperature is kind of monotonic. So that's how it started. And as anything in science, it's a very inductive way.
But then it should be the other way around.
Sorry. Yeah, it's. Yeah, thank you. Oh, good. Now, that's really what I want. Questions, corrections, delivered all the time. Yes, of course, it's restricted from below. And as we would now say that this is something that is a change of quantity, which we later call entropy by Clausius, must be larger than the change. So this reservoir lost this amount of this quantity, which is heat divided by temperature, and this amount gained, and the gain must be larger than loss. Okay? And just to give you a trailer of what will be later in the course, in the lecture 3, how we now look with exactly the same scheme, for example, on a living being, on a plant or animal. What something which is alive needs to sustain life. And a normal person would say it needs energy and matter. And a scientist would never say this, right? Because we know that energy is conserved and matter is conserved. We cannot consume energy and we cannot consume matter. We just get some matter and we get some matter out, and it's exactly the same amount of matter as long as you aren't a child and you aren't growing. And energy is the same story. You get some energy out. We do not consume it. So what do we consume? Living beings. We consume information, entropy or order. We need this energy to pass through us to maintain order, because we are a combination of atoms which is in a very unlikely state to be. To keep our set of atoms in the state that we are, we really need all the time to get this entropy out or information in, which means that what is life? Life is something which interrupts a flow of entropy from a low entropy reservoir to a high entropy. Okay? And then you may ask now a different question. You may ask, what would be this S2 minus S1? Because that would be, now I'm looking at the same delivery of information, so how much would be S2 minus S1? Or you may ask, what would be the price, how much energy you need to pass if you want to get this information, and then you discover that it's this, let's call it delta S, plus work divided by 1 minus T2 minus T1, which is, of course, exactly what you get from here if you satisfy this inequality. So the criterion of Carnot tells you that you make your engine more efficient, but you cannot make it better if you really make this ratio very large. Now, what this tells you, that if you really want your price to be smaller, you need to make, again, the same thing, this T1 to be very large. How plants do it? Plants get energy from sun. Is sun a low entropy source of energy? What do you think? Low entropy. Yes, it is a very low entropy source of energy because it has a huge temperature. A temperature is always in the denominator. So when you look at this formula, which is the energy price of information that you get, and T1 goes to infinity, or getting very larger than T2, it disappears. And the only thing that is here is how much you lowered your entropy. And unfortunately, we need to do some work. Well, your generation already get information doing very little work, just a finger moves. But normally, you also need to do some work to get information. So what I really want you to see is that this exactly the same scheme brings us from 1820s to this century, so 100 years, without much change. But to get from here to here, we needed to understand entropy, which appeared kind of semi-empirically here, in a way which connected it to information, and this is essentially what I'll be talking about. And it's done on different levels. The simplest way to do it is purely phenomenological, and it's called thermodynamics. Thermodynamics is a way to look at some system for which we do not know what is inside, but we don't follow what is inside, but we know nature of what is inside. It could be atoms or spins or neurons or market traders. We know what kind of constituents of this system, and we know some symmetry, some invariance, some conservation law of the system. And classical thermodynamics started from symmetry, which is time, translation invariance in time. And it was a conservation of energy which corresponds to this symmetry. So it says that we have a thing. So now we're doing thermodynamics. And it starts from the first law, which is essentially a statement that you have states of your system, and you can connect any state to any state in a way that you know all the energy changes, namely that only work happens, no heat exchange. In this way, you can ascribe to every state of your system, we will be usually calling it I, a definite energy. And then, when something happened, and you find that the change of energy is not equal to work, let me call it like this, then you call their difference heat. So work is a change of energy of a degrees of freedom that we follow. Here, you see how information, the idea of information, something that we know sneaks in. It's like idea of probability sneaks in through credit. And we call this difference, this is essentially a statement that we believe in conservation of energy. That's the first law of thermodynamics, which means that if you're doing thermodynamics for a new system, for a cell, for a market, for a field of economics or anything, you need to ask what will be your energy. And it's not easy because, for example, if you're working with living beings, that the laws that govern their behavior change with time. My body is now governed by different laws as 45 years ago when I was looking 18-year-old at Zahara for the first time. When you're working with a market and you tend to treat money as an energy, it is. When I give you money, I have less, you have more, amount of money is conserved. But when you look at society, you will see that the amount of money in a given country, particularly in this country, but in my country too, just grows. And it more looks like entropy. So it's not trivial to do thermodynamics. We used to think about it as a simple science. The moment you start doing it yourself in your research, and this course is an essentially invitation to research, just to show you how many subjects. So it's non-trivial. But this is essentially first law. It's a statement we believe in conservation of energy. Nothing else. That's it. And then the second law, it's even more huge jump from what Sadi Carnot invented. It's a deduction. It's a deductive statement, which says that there exists a function of energy. Of course, it's it comes from here. And this function is monotonically growing. Or if you take a system which is under constraint, you remove constraint, you wait for a while, then you find out that this quantity increases. Only thing that you need to know in thermodynamics, it is this function. If you know this function, you know everything. You can solve what is called the basic problem of thermodynamics, namely to what state any system evolves if you remove constraint. What kind of function? Monotonic? What we would expect, this function? How it would look like? First of all, the statement is that there is some equilibrium states, so that all other states are below. So the world exists over here, right? And then there is some line and nothing above. Okay, so you can go up to this line, you reach it, it's your equilibrium. The question is, could it be like this? What do you think? How's your intuition about it? Well, this derivative, it's what could be read from here, right? This is your energy change. This is your temperature. So you may say that this is, essentially by definition, it's 1 over temperature. Could temperature be negative? Any laser physicist here? Okay, maybe in 20 minutes we'll get a negative. Yeah, there could be negative temperature for any system with a finite phase space. Now I am jumping through. I don't want to really, at this point, to go into much detail. What I want to show you is that you are a scientist the moment the temperature is not a thermometer that you put under your arm. It's a derivative of energy with respect to entropy. That's it. That's the most important thing. You start thinking thermodynamically the moment that for you temperature, it's this derivative, and this derivative could be negative because, you know, a phase space could be such that as you increase your energy, you have a less and less space, and then your entropy actually decreases. And what is really important is that it's convex. Convexity is the most basic property of practically any function which appears in thermodynamics, statistical physics, and information theory, and I really want to convey it. There are maybe, at the last lecture, we'll have the take-home lessons. There will be like 5. And convexity will appear like 3 times in this 5. Why would we need this convexity? Well, first of all, we need convexity to have one-to-one correspondence between, to have this derivative really defined. It's important. On the other hand, we may, so when you look at it, you say that, let's say, for now, to look at this left part of it, but what it tells us that our world is here. Here is equilibrium, and you can reach equilibrium in 2 ways. Under fixed energy, you can go up in entropy, or at a fixed entropy, you can go down by energy. So the same point of equilibrium could be treated as minimum of energy or entropy. That's it. All thermodynamics is here. What is left is to get this function. You can either try to get it experimentally, namely you look in what is called equations of state, namely what are changes, or you can try to derive it, which we also do. But there is some point which we really want to have an alternative description, and this alternative description is that we want to have something which would be function of temperature and not say a function of energy or entropy. As thermodynamics say, those are extensive variables. When you make your system twice larger, your energy is getting twice larger, your entropy is getting twice larger. But the derivative is not. Derivative is an intensive variable. So let me turn this thing. So now if I would have energy as a function of entropy, it's some concave function. I'm just inverted this function. But I would like, instead of it, consider something which is a function of temperature. Of course, I may say that this is an equation that I have, and this is some function of E. Or I can look here and say I have a derivative of energy with respect to entropy, and this is the temperature, and I know this function. So I need to take energy as a function of t, as a function of s, and that would be it. Well, that would not work. Why? Because if temperature is a slope here, right? So if I defined energy as a function of this slope, then for this slope it is this energy. For another slope it is this energy, right? But on the other hand, if I take curve like this, which is exactly parallelly shifted, it would have the same dependence. Again, the parallel slope would give me the same energy, and another slope again would give me the same energy. So what French mathematician invented for us is this Legendre transform. They say, you want to fix this curve. Just you want to somehow fix and not have a family. So there are many ways to, but one of it, and this is something which appears over and over in thermodynamics and in information theory, is called Legendre transform. And it says, let's characterize all such curve by this point. Because if I fix this point, then I fix this curve. Now for every t is a slope, right? This is my t. I would have a different point, and I call it f. And it is, of course, e of this minus t, my slope, times s. This is my coordinate. So appears something which we call free energy. And it is a fundamental object. It's a Legendre transform. Now everything here is a function of temperature. And this is something which is very convenient if you want to describe a situation under a constant temperature, namely a system in a contact with a big thermostat. Why it's called free energy? Well, there are no free lunches, or there are free energy. And what does the term free means? And when I was a student, the explanation that was given by brilliant lecturers at Novosibirsk University was because that how much we can free to use for work keeping the constant temperature. You cannot use all your energy for work. You need, it's less than your total energy. That's why it's free. It's what you're free to use. When now I teach this thing, I'm teaching it also, I'm saying, this is how much we do not know about a system. And as long as the more we don't know about a system, the less energy of it we can use. And essentially all this change from 20th century, well, actually from the beginning of 20th century to the end of 20th century, was this shift in emphasis from what we can do, from what we do know or do not know. Okay? That's all of thermodynamics. How much time I get? In 20 minutes, I'll tell you all thermodynamics. Now let's try to do about the same with the statistical physics. And this is actually a reminder. I think that more or less you've seen such thing. So how statistical physics work with it? You now want to derive it, not to guess. For this, you really need to look under the hood and ask what is actually the elements of your system. But you might try to do it in a pretty generic way. And this is, of course, Boltzmann, who started this thing. So you can say, what is actually this S if you take an isolated system, and at least you know that this system has some number of states. Initially, it was called gamma, but then we would be almost always call it n because it's kind of more intuitive. But you know, to honor Boltzmann, let's call it gamma. And Boltzmann wrote the formula, very simple. It cannot be simpler. And I write it with the Boltzmann constant. And it's, if you'll be in Vienna, it's a very beautiful tombstone of Boltzmann. The most interesting part of Vienna is cemetery, where this formula is written. This is maybe one of the 5 most important, maybe the most important formula ever written. At least technically, this is the most important formula ever written. And it claims the following things, that of course gamma is the function of energy. when you raise energy or lower energy, you can get more states or less states that have this energy. And entropy is a logarithm of it. That's it. That's a statement. Okay. Now, how would you solve a problem of thermodynamics which says that take a system, let's say, and remove the constraint? Let's say I let heat pass through these two parts, and I would like to understand what will be a state of such a system, right? What do I know? I know the second law of thermodynamics. So let me just, which notation I would use? Yeah. I would, so what you know, that energy, the first law of thermodynamics tells you that whatever there is energy changes, there must be like this. If you get more energy here, you must get less energy here, the total energy is conserved. On the other hand, what you do know, that if you look at the entropy change, it is ds1 over dt1 de1 de1. That's a change of entropy. It's a derivative with respect to energy, plus ds2 over de2 de2. But this de2, it's minus de1, right? Because of energy conservation. So what we find out is that it is 1 over t1, it is this derivative, minus 1 over t2 times de1. And it must be positive. That's the second law of thermodynamics. That's how you solve the main problem. It tells you that if this must be positive, and dE1 is positive, namely energy came from here to here, this is a possible process only if this is possible too. And to be this possible, you need T1 to be less than T2. Energy flows from hot to cold. That's a relief. It at least corresponds to our understanding. And equilibrium would be T1 equal to T2. How Boltzmann solves the same problem on a microscopic level? He says, OK, let's take this system, which consists of two parts. And maybe I'll use a blue one now to switch gears. And let's write it how many states are for different partitions of energy between these two parts. Okay? So what I'm actually saying, that my gamma as a function of energy, and I assume that there is some portion of energy, and it's a very, very sneaky way to introduce a very, very important concept. But it's really important that energy now could go in portions. Namely, I have a state in which here I would have 0 and here E. Or I have a state delta E minus delta. And the whole enchilada until, so I would have a sum over I from 0 to E divided by delta. And it will be gamma of E y and gamma 2 of E minus E I. Okay? So I need to take how many states in a position like this, how many states in a position to this, and this will be the whole number of possible states when my whole system has this energy. And then what Boltzmann say, and this is a very, very important and simple step, but very profound. He said, let's look at the maximum of this sum. It's a sum of many terms. Let's look at a single term, which is maximum. So what I shall be doing, I would be differentiating d gamma over dE and looking for 0, right? So what I would get d gamma 1 over dE1 times gamma 2. So I differentiated this times this, and plus d gamma 2 dE2 times gamma 1. And it must be equal to 0. And of course, what it is, it's gamma 1. And remember that gamma is exponent of s, right? So now if I differentiate, I would get it gamma 1, gamma 2, ds1 over de1 plus ds2 over de2. And of course, those are temperatures, which exactly appeared over here. 1 over temperature, right? So here you get it phenomenologically, and here you get an equilibrium condition as a condition of a maximal phase volume. Okay, that's it. That's a, a technical step. So you would get equilibrium at T1 equal to T2. Okay, good. Now, how I'm doing this time? Excellent. Now, in principle, we can compute it. And because we discussed this question, could our temperature be positive or negative, let's consider a simple system, which is physicists call two-level system, but it could be neurons, it could be spin, anything that can have two states. A neuron could be in a state not firing and firing. And it's a very, very rich field of application where you consider two-level system. Or you can consider spin up or spin down. Or you can consider your logical element in a state of 0 or 1. And now you say that if you divide your energy divided by delta by this epsilon, this portion, let's call it L. So this will be my analog of energy. I want it dimensionless. So my gamma as a function of total number of spins and or total number of systems and energy L, that would be analog of volume and energy, must be just simply binomial coefficient, how many ways to pick out of n, L, and of course it's n factorial divided by L factorial divided by n minus L factorial. And if you take a logarithm of it and you consider limit when n and L very large, you can use Stirling formula, and I'm just skipping all this. So you obtain your entropy as, let me write it in this form, n logarithm n minus L plus L logarithm n minus L divided by L. If you now plot it, entropy as a function of L, which is my energy, right? So you would see that when your L going to 0, you would have this 0. You would have this n minus L would be L, Ln also will be 0. You would have here unity, which is again be 0. So you start from here. On the other hand, when your L equal to n, it's a totally symmetric situation. It's symmetric with respect to Ln minus L. So you're again here. It's already clear that it's a convex function. It is like this. It's convex, but it's not monotonic. And that's exactly, so now when you ask what is here, you remember that ds dE is 1 over T. So here ds dt is 0, which means that your temperature is infinite. Well, yes and no. It's plus infinite here, and it's minus infinite here. Okay? And this is exactly what is the simplest thermodynamic description of a laser, because it's here your system generates, and here, of course, your temperature is 0, and here your temperature is minus 0. Okay? So this is an example of a probably simplest physical system. And what we did simple combinatorics, and we derived the entropy function. And also on the way, we learned about the negative temperature. Now, it's not only way to treat things, because as we discussed, we may try to work not as extensive variables, namely how energy depends on entropy or entropy depends on energy. We may try to work with a what is called canonical ensemble, which is a very bad term, actually. It's very confusing. We actually want to work with a system under a constant temperature, in a contact with a thermostat, a system which is not isolated, like Boltzmann did, but a part of something. How, in this way, we can connect, because we know that such system must be described by free energy, and we want to connect it to statistics. And this was done by Gibbs. And again, I'll probably switch into yet another color to distinguish between different situations. It's beautiful to have that much space. A dream of a lecturer. You're very fortunate people. So now I would have a big thermostat, and I would have my small system inside. How I call it? That would be called E naught, and this I would call energy E. And I would like to derive what is the entropy here. And here appears the most important formula, at least of these 5 lectures. So let's see how it appears. So I would like to say, to ask what would be the probability of having a state of my system, this one, well, it's, sorry, let's say having some value to be on some state I. What is, you can naturally assume, again, you're working after Boltzmann, and you would say that we don't know anything about what is this type of system. Here is again, we don't know, for about 100 years was considered as like a part of sentence which we say very fast until nobody knows it, and they'll never return to it. We'll return over and over to this fact. We don't know nothing about the system except its energy. So we assume that all states of this which could realize this energy are having equal probability. Namely, we assume that this is proportional to the phase space, number of state of our thermostat having the energy which a thermostat has, which is E naught minus E. So it's gamma of thermostat, which is huge, and our energy E, which is small relatively to it. This is a very, and of course Gibbs perfected it, assuming the thermostat is created of copies of our system. There are many beautiful mathematical tricks, but we don't need them now. It's just a simple statement that probability of any state is expressed through the phase volume of a thermostat having energy minus this state. But now, because this is small, we expand. The question is what to expand. The Russians like very much jokes about Landau, who always says that the most important thing is what is in the exponent, not the prefactor. And once some from his student caught him counting money and said, Landau, you say that you need to estimate things, not to count exactly. He said, no, money is in the exponent. Money, like entropy, is something which is in the exponent. And Gibbs knew it from Boltzmann. So you expand it in the right way. You write it as an exponent of s minus s, where am I? Yeah. S, let me write it like this. S of thermostat at an energy E naught minus E. And this function now you expand. Okay? And entropy always will be something in the exponent which determines the rate. That will be the main message. So let's now do it. And of course, it would be exponent of S naught taken E naught minus, not surprisingly, E over T, right? Because the derivative of S with respect to energy is 1 over temperature, right? It is that as simple. And of course, it's a Gibbs distribution. You can you can write it as an exponent minus E over T divided by normalization factor, which is, of course, the sum over I over all possible states, right? So you want this probability to be normalized. And now you need somehow to relate it to your thermodynamics. Where is free energy here, right? And you relate it in the following way. You say that now there is no definite entropy of this system because energy here fluctuates, and this is the probability of these fluctuations, right? So you want an entropy of the system, you need to compute a mean entropy. So you say that your entropy in a thermodynamical way would be a logarithm of 1 over pi. This would be your total number of a given state, averaged. What does it mean, average? It means you sum over all I minus pi logarithm of pi. Good, that's your pi. Here it is. Let's plug it. It will be minus sum over pi. And if I take a logarithm over here, it will be ei over t plus logarithm z. Okay? And minus disappeared because I have minus over here, and this is in the denominator. Well, of course, pi ei is just an energy, right? So it will be E over t. And what is the relation between entropy and energy and the free energy? It is this relation, right? So we want S to be from here E over t minus F over t. So we need to identify what is standing here with a free energy. Okay? So we need to say that the free energy is a t logarithm z. And that ends statistical physics. That's all thermodynamics, that's all statistical physics. But what we come out, which did not look initially like a very big deal, it is this formula. And this is the most important formula. It's called Gibbs entropy. And of course, it would appear over and over and over again. This is an idea that what appears is not of logarithm of a number of state, but a mean logarithm of a total number of state. Okay? So that's in 39 minutes, thermodynamic and statistical physics. And now we need to make sense of it. Because if you stop for a moment, it looks very strange. What is strange here? What is the most bizarre part of it, if you look at it?
No dynamics.
There is no dynamics here, but of course, we say something important about dynamics. We say, we draw this picture, which said that if all states are here, if we let system evolve, it would creep to this state and then would stay over there. So we derive some quantity. First, we postulated it phenomenologically. Then we made some hand-waving argument that it is somehow about counting number of states, which is just counting, right? And then we say that this quantity must grow if you let system evolve. How? And that brings the second way of thinking in this discipline, which is totally different from what we did here, namely, if you think what technically we did, it's essentially simple combinatorics. We say, oh, you just counted number of states, or we just wrote, where is our binomial formula? Yeah, that's it. That's the most complicated formula that we wrote so far, but this is a discrete combinatorics. It's mathematicians, by the way, pure mathematicians, believe that this is one of the most difficult mental activities. You know, there is this hierarchy, they used to say, okay, it's like a smartest boy in the class will be a mathematician, but then inside this group of mathematicians, there was the smartest people who really can classify and count. It's a very complicated mental activity. But what I now want to show you that to understand all this, you need another way of thinking, which is totally continuous. And this is a way of looking at flows. And this is something which appears already only in 20th century, and this makes sense of what is actually happens when we drift from here to here or from here to here and we reach a maximum of entropy or a minimum of energy. And this is idea, I don't like to erase it, I really like it very much, but probably don't have much use. This probably will be inconvenient, right? If I would, yeah. Yeah, maybe let's erase here. So what now I'll spend last 10, 13 minutes is to give this idea, which is of course the idea of dynamical chaos and coarse graining. There are two very powerful ideas, which tells us that really, if you look at a system which evolves in the most precise and beautiful way, namely a Hamiltonian system of exact dynamics, which is a very conservative, you'll get a growth of entropy. So let me give you this brief illustration. Essentially, let's now look at our space of coordinates being P and Q, and there is as many of it as we want, like 10 to 23 coordinates and momenta of particles, and they satisfy the equation, which are Hamiltonian equation, which says that there exists some function h of pq. This is the most general description of a conservative system because of power of canonical transformation. This is really the way that. But what is important is that the equation has this form, dh dp. So if you define a velocity in this unbelievably multidimensional space, which would be a 2n dimensional vector of p I dot and q I dot, and then you take a divergence of this velocity field. A divergence means that you differentiate over all coordinates. So you sum and you differentiate it over all qi's and you sum. And of course, when you differentiate this with respect to p, you get a mixed second derivative. And we differentiate this with respect to q, you get a mixed second derivative with the opposite sign. And this is 0. It means that the flow of, so your system starts somewhere and then starts moving. Your coordinates change, momenta change, it evolves. This dynamics is an incompressible flow. This is a rate of expansion or compression, and it's identically 0 everywhere. And this is a very important point to understand how the hell entropy can grow. So if we now look at in a continuous way of the density or probability distribution of in this multidimensional space, of course it satisfies continuity equation. It's a density or probability, it's conserved, so it's d of rho v. But we better like it to write it in the following way. If we write it following the flow, it has the form which is like this. This is just a derivative along the flow, d rho dt plus v grad rho. Of course, here all the derivative over all the coordinate and moment. These are our coordinates in space. So when dv is 0, rho does not change. Neither expand nor contract. Okay, it's a so now, of course, if rho does not change, entropy does not change. It's called Poincaré theorem or Liouville theorem. This Poincaré invariant is called Liouville theorem. So our rho does not change, and dynamically it is something which is apparently seems to be contradicting our statement about entropy, because this evolution is invariant with respect to time. If you change sign of time, you may change sign of Hamiltonian, it will be the same system. But then you need to understand, again, this crucial sentence which always and always appear, as far as we know and how much we do know. So if we now say that what we know here, it's the initial position of our given system. Let's say our rho is not a delta function, but a little bit spread, because we never know it precisely. We always know it with some accuracy. And then we ask if we would start, then there would be different trajectories coming out of here. And the most important statement which comes out of a very general theory of this dynamical system is the following statement, that practically any system which has more than 2 degrees of freedom would have this trajectory separating exponentially. Moreover, if you look at the generic flow, which make it some direction them separating, then coming together, then separating again, then coming together, so there's many different things happen, net result would be always separating. Let me explain you how it comes out. And the crucial thing which is important for this statement is the same property of convexity, which appears in different ways, and here it appears as following. Imagine that you would have a separation with a rate lambda, but this lambda could be positive and negative. In particular, it could be with equal probability on your evolution, positive and negative. So if you're interested in the average rate, so you started from some, and you just need to integrate over all positive lambda, let's say from minus a to a. Okay? What can we say about this integral? You see, lambda mean value is an integral from minus a to a of lambda, and this is 0. But this is a convex function, right? And so you will find out that this thing, which is exponent a minus exponent minus a divided over 2a, right? And it's always larger than unity. I intentionally skipping a very beautiful mathematics. I'm trying to give you the simple basic feeling how it's possible that essentially whatever is inside the system, it's a very, very generic statement. Then you would always have it. There is another way to look at this, maybe the most beautiful part of this science is called oscillated theorem. And let me know why, if you really have this expansion and contraction, how you can explain that eventually it will be non-stopping expansion and separation. And this is the following thing, that it's incompressible fluid, right? So you started from some initial ball of your initial data. You don't know where your system inside. After a while, it evolved into something like this. If it's expanded in some direction, it's necessarily contracted in other direction. You see how important here is my incompressibility, my conservation of volume. Now, with time, you would meet contraction and expansion in different direction. But to return back to this shape, you need that your contraction acts. You see, if this is my original circle, and I want to return back to it, my contraction must come now in this narrow angle, right? Because if I contract outside of this angle, it will be further expanding into this direction. So my contraction now is much less probable to return me back. And that's a basic mechanism of its beautiful mathematics. I mean, I'm not giving justice to the way people really proved it, but this is the intuition behind it, okay? And as always, you can look at it in terms of convexity, or you can have this simple geometrical picture out of it. Or sometimes, for example, it helps people just to look into a simple flow, like just simple hyperbolic flow like this. And you say, this is my original position, so if I start from this vector, what would happen with it? It would approach this point. Yeah, it would approach. It would go like this. If I start from here, well, it would expand. It would go like this. Okay? And then you ask, if after a time delta t, I would change kind of directions or whatever, that what will be more vectors during time t, expanding or contracting? And then you realize that there is some angle which is exactly symmetric to this angle, so that during time t, you come from here to here, right? And then you realize that all the angles over here behave differently from angles over here. That's what gives you, it's another example of convexity. That's what again gives you this asymmetry, which tells you if you're doing it in a very random way, but with a finite time step, it would be eventually always, they would all run away, they would all separate. So essentially the mechanism by which phase volume grows is the following. You start from this thing. After a while, you evolve into it. After a while, you evolve into this. This is a non-stop process. You can also bend it. But your resolution stays the same. It is this resolution. Right? You aren't improving your resolution as things continue. So now, from your viewpoint, it is this object. And of course, it has much phase volume. Okay? So this is the last thing which I want to end. So let me reiterate a take-home lesson from this lecture. First of all, the whole idea appeared trying to set limits of what is possible to do. That was a driving force. It led to understanding that there is some kind of an inequality behind which some irreversibility is hidden. And it brought us the idea that this quantity which measures how much irreversibility in the system, this quantity is related to the logarithm of number of states, or more generally to this mean logarithm of the number of states. And that's end of introduction, and next lecture will be information theory, which retells all the story in a different language and applies it to everything. And to apply it, to choose a subject, I really need your help. So what we have a piazza space where I posted a lecture notes, and I want you to treat lecture notes at this moment as a menu. Just look at the content, because you can have market strategy, or bacteria genetic switching, or black holes, or optic things. So I don't know what would be more interesting to you, because I can illustrate these ideas and information, or you'll be interested in communication, or in languages, or in genetic code. I want your feedback. Then by the lecture 2, 3, and 4, we can more or less choose what will be most interesting set of subjects to illustrate these ideas.